Imagine designing an algorithm to build a digital layout. You have dozens of interface elements, and you need to arrange them to maximize their overall value without letting conflicting pieces overlap. A common starting point is a recursive function. You tell the system to start from the top and systematically test every possible arrangement, branch by branch, looking for the absolute best fit. But as the number of elements grows, the system stutters and eventually halts. It throws a terminal error: maximum call stack exceeded. This happens because of overlapping subproblems. Because the recursion tests every branch blindly, it ends up computing the exact same localized layout combinations thousands of times. The redundant calculations scale exponentially, overwhelming the processor. To fix this, developers often try memoization, caching the results of those subproblems, but the structural flaw remains. The system still has to maintain a deep vertical stack of paused functions in its active memory. If the layout is complex enough, you'll breach the memory limit before you ever finish the tree. Caching a top-down architecture is often insufficient for high-dimensional problems. Truly solving an exponential collapse requires reverse engineering the entire processing model. This is where 1D tabulation comes in. We abandon top-down recursion entirely and build the solution upward, starting from the absolute base cases. Take a $1,000 ad layout. Rather than calculating the entire grid at once, we break it down to evaluate the smallest, simplest possible subcomponent first. Represented as a single, one-dimensional array, the algorithm evaluates one slot at a time. Each new slot follows a deterministic transition rule. Skip the item and inherit the previous maximum, or take the item and add its value to the result from 2 steps prior. Because we build from the bottom up, each subproblem is solved exactly once before it's needed. This guarantees the calculation finishes without ever risking a recursive stack overflow. In 1D tabulation, the direction of memory iterations serves as a mathematical enforcement of the data's physical constraints. Consider an unbounded knapsack problem, a scenario where a resource or layout element can be reused indefinitely. For infinite reuse, we iterate forward, allowing current updates to cascade into the next cell. But for single-use constraints, forward iteration double counts resources. We fix this by forcing a backward iteration to 0, referencing only isolated prior values to preserve the single selection rule. The choice between a forward or backward loop isn't just a coding preference, it's the mechanism that aligns the software with real-world operational logic. We can refine this architecture even further by looking at the underlying C++ transition rule for our layout. Looking at the logic, the calculation for the current state only ever requires the values from the previous 2 steps. This allows for total space compression. We can drop the massive memory allocation of the full array and replace it with just 2 alternating variables that leapfrog each other as the system iterates. This reduces the system's memory footprint from linear to constant, O of 1 space. We've eliminated the scaling cost of memory while maintaining efficiency. This exact 1D sequential projection scales far beyond basic software algorithms to solve massive engineering bottlenecks. In Android UI design, flattening deeply nested container hierarchies into single-level coordinates eliminates the multi-pass layout and measure loops that cause rendering lag. In physical engineering, multi-thousand-dimension thermochemical simulations in fluid dynamics are often projected onto a flat 1D grid using flamelet-generated manifolds. This projection reduces complex fluid simulation times to roughly 1/160th of their original duration. By translating multidimensional dependencies into flat, sequential tables, architects can bypass severe execution bottlenecks and improve the operational scalability of complex systems.